So Dr. Robert Dimeo is the director of the NIST Center for Neutron Research, which is a national user facility for neutron scattering on the NIST Gaithersburg campus. Dr. Dimeo received a Master of Science in Electrical Engineering in 1994 and a Ph.D. in Physics in 1999, both from the Penn State University. He joined NIST as a beamline scientist for the high-flux backscattering spectrometer instrument that same year. In April of 2010, he became director of the NIST Center for Neutron Research. And based on my unofficial history, Rob was the youngest laboratory director in the history of NIST. His research interests include the dynamics of quantum fluids, quantum rotations, and molecular solids, software development for the visualization and analysis of neutron scattering data, and the development of neutron instrumentation. From 2005 through 2007, Dr. Dimeo served as the Assistant Director for Physical Sciences and Engineering at the Office of Science and Technology Policy. That's out of the White House, of course. There he was responsible for working on policy matters involving major research facilities in material science across the nation, interagency cooperation on large-scale research activities, and other interagency working groups. Remains active in U.S. science policy to this date. His topic this morning will be True Stories Told with Neutrons, and he'll share with us some research opportunities at the NIST Center for Research, Collaborative Research there at the NIST Center for Neutron Research. But before he speaks to us, and John, can you put up the next slide? I'd like to share with you one of his many other talents. He is an excellent listener and sketch artist. He has shared with me some of those notes when I gave a few years ago a lecture on the African American contributions to the history of NIST. And basically, right after that, he gave me this sketch, and it was unbelievable. And I was totally blown away. And hopefully, you see there an example of the notes he took at a recent lecture there at NIST. So, the real trick will be to see his notes from today's seminar. We'll see if he can do his sketching and doodling as he speaks to us. So Rob, are you ready?
I am ready, and hopefully my tech works here, Willie. Thanks very much.
Okay, thanks so very much for taking your time to share this seminar with us and to expose to Morgan some of the opportunities, some of the unique toys you have built there, and some of the possible opportunities for collaboration. So Dr. Dimeo.
All right, thanks very much, Willie.
And I see you got on one of my old shirts.
Yeah, yeah, I got the NIST uniform on, Willie. You recognize this one for sure. So thank you, Willie, for inviting me for this opportunity, and thanks to Dean Yu as well. I'm going to stop my video, and then I'm going to share my screen now on the presentation that I have for you. So just give me a moment while I get this up here. Okay, and can you give me a verbal indication that you can see my title slide here, Willie?
Can see it.
Okay, perfect. So thank you very much. So I'm really excited to be able to give this presentation to describe what it is that we do at the NIST Center for Neutron Research, or NCNR. I'll use that term, use that acronym throughout. So during this talk, Willie was interested in hearing me presenting a little bit about the history of the NCNR. And so, typically I don't do that, but it is an interesting history. I'm going to keep it brief, but it's an interesting question to answer. How did NIST come to have a nuclear reactor? And it's sort of a fun answer to that. After that, I'm going to talk about the key features of this National Scientific User Facility. Then, of course, the power of neutrons as a probe of materials. And then my favorite part is going to be to tell you what I call true stories told with neutrons. And these are the real research opportunities at the NCNR, in which I'll describe, I'm hoping to get through about 5 examples of scientific research that took place using the NCNR instruments, including one scientific highlight by a group from Morgan State. And as Willie mentioned, I have this proclivity to doodle quite a bit. So throughout this presentation, you may see an occasional doodle or two here. I like using the technique of hand-drawn sketches to explain scientific principles and to add some emphasis to things. So bear with me as we go through and do that. My assumption is I understand we're supposed to have a relatively broad audience. And I'm assuming that most of you are not familiar with neutron scattering. For those of you that do know neutron scattering, some of this is going to be a refresher, but I'm sure you're going to enjoy the science highlights and hopefully learn something new in this presentation. So I have to show the obligatory or organizational chart of what NIST is and what the NIST mission is. We promote U.S. innovation and industrial competitiveness by advancing measurement science, standards, and technology. And the key part of the NCNR is the advancing measurement science part of that. And we do support quite a bit of academic research as well as industrial research. The NIST is broken off into measurement laboratories, technology laboratories, and user facilities. I've listed our 2 measurement laboratories, our 3 tech laboratories. Under user facilities, we are the only operating unit that is completely dedicated to a user facility. There is the Center for Nanoscale Science and Technology that has a nanofab facility, and that's part of the physical measurements laboratory. In the NCNR, our mission is essentially to provide neutrons for the U.S. scientific community to do research here. And you're going to see several examples of this as we go through. And we're going to start off with a little bit of history. So how did NIST, or actually back in the day, the National Bureau of Standards, come to have a nuclear reactor? And it's an interesting history. The planning for the reactor actually began back in 1957 when the director of the National Bureau of Standards, Alan Aston, and Department of Commerce Secretary Lewis Strauss got together and started talking about what we could do, what NIST or NBS could do with a nuclear reactor. And this was part of the Atoms for Peace initiative going on throughout the United States. And there were other things going on in the U.S. as well. In particular, Brookhaven National Lab and Oak Ridge were also looking to develop their own reactors for their purposes. The high flux isotope reactor, as it came to be known at Oak Ridge, was a reactor optimized for isotope production. The high flux beam reactor at Brookhaven eventually came to be known, was optimized for science with beams. And that's really what the NBS folks were interested in, was science using neutron beams, high intensity beams. And so in 1958, the decision was made. They were going to build a reactor on the new Gaithersburg campus. Interestingly enough, I was fascinated to find what the initial costs for this were. So $700,000 for the design of the reactor back in 1961. Obviously, these have not been adjusted for inflation. These are the original numbers. And then in 62, $8 million for the construction. And as I look at new research reactors that have been built recently, you know, this is a couple of orders of magnitude difference. You know, the last one that was built in Australia, in Australian dollars, which is comparable to US dollars, was of order 500 million. There was a nice article that appeared in this Nuclear Power magazine talking about NBS's plans to build this, but also planning the use of a cold neutron moderator. And I'm going to talk a little bit more about that, but that turned out to be a very key decision. So in the early 60s, ground was broken, and you can see in the upper left-hand corner here that there was they built the original building was constructed for offices first, and then the reactor building with all the scaffolding on the side of it came to be. To the right of that is the reactor vessel, and an interesting feature of a research reactor that's built for beams is you put holes in the reactor vessel, because that's where you let the neutrons come out. So that's a unique feature, because most of the time for power reactors, you typically don't have those kinds of holes in there for letting neutrons out. You try and keep all the neutrons in. In 1967, they achieved first criticality and brought it up to full power at 10 megawatts in 1969 for regular operations. And I included a picture in the lower left-hand corner there that shows all of the folks in the control room, including the three original founders of the Center for Neutron Research, and I'll show them to you in a subsequent slide closer. But that bottle of Chianti is actually was a tradition whenever a new reactor was brought critical for the first time, and that was harkened back to the days of the first criticality of the first reactor in the first pilot experiment at the University of Chicago. So the three founders of the Center for Neutron Research were Bob Carter, Carl Mulhouse, and Harry Landon, and they essentially designed this reactor purpose-built for neutron beam work, some trace analysis, some standards work, but primarily for neutron scattering and materials research. They built it they designed it with analog techniques. But one of the key decisions that they made in the early period of the design was to include, if you look at the bottom photograph, there are a number of thimbles that are poking into the reactor vessel. So we're looking down into the bottom of the reactor vessel right now. And that really large thimble that the arrow is pointing to was the critical decision. That was where they, at some point in the future, wanted to put a cold neutron source. And I'll explain a little bit more about that later, but they didn't put the cold source in at the outset of the reactor. In 1970, you can see that it was quite the greenfield site. This is Gaithersburg, which, as you can see in the photograph below, is now quite built up with a community, just a few hundred yards behind the Center for Neutron Research. The progression of history is we increased the power in 1985 from 10 megawatts to 20 megawatts, which required a reactor license change. And then the first cold neutron source, which was heavy ice, D2O ice, was installed in 1987. And then the management and leadership was able to get funding for a new cold neutron guide hall in 1989. And then subsequent improvements in the design of the cold sources resulted in a new advanced cold source in 1995, then one that was even higher performing in 2002. And then the status in the United States as of about 2007 was that the scientific community was being dramatically underserved by the existing neutron user facilities in the country. And so this included, for example, Oak Ridge's neutron sources, the NIST neutron source, and several others around the country. The demand was just enormous. And so NIST was able to get funding to build a second instrument hall, and I'll show you a schematic of that shortly, to improve or increase our neutron measurement capacity, in particular the cold neutron measurement capacity. Okay, so let's talk about the scientific user facility, and also let me explain what I mean by cold neutrons, because I've been using that term quite a bit, and it probably, if you don't know neutron scattering, it probably means very little to you. Our instrument hall is composed of two physical structures side by side, and then the confinement building. On the left-hand side of this slide, what you'll see is a squarish building. That's our confinement building, and all of the instruments in there, save one, are viewing the reactor, and they're seeing thermal neutrons. So these are neutrons with energies of tens to hundreds of millielectron volts. Except for this one labeled max. This has its own little dedicated cold source, and so it's seeing neutrons with energies of order millielectron volts. Now, at the 3 o'clock position on the reactor, there are a bunch of neutron beam lines radiating outwards towards the right. Those are all viewing our large 5-liter liquid hydrogen cold source. So all of those beam lines are being fed by basically millielectron volt to 5 millielectron volt energy neutrons. And it turns out that thermal neutrons are very good at seeing higher energy excitations, vibrations, torsional oscillations of molecular systems, whereas the lower energy ones, more in the micro electron volt to millielectron volt range, can see slower motions. And you're going to understand why that's important when we start looking at some examples. Our beam hall is pretty full. This beam hall shows 30 beam experiments. We are oversubscribed. We operate 240 days per year, and when we're operating, it's 24/7. We have folks coming to do experiments from all over the country, in fact, all over the world. We've had to take a pause, obviously, for the pandemic currently, but when we are operating in a normal mode, we have a significant amount of people coming from other parts of the country. So reactor reliability matters a lot to our users. When they get on the airplane and come to Gaithersburg to do an experiment, they expect our facility to be running when we say we're running. And our output, we serve, actually it's up to about 3,000 research participants per year we serve, and around 350 pubs per year is one way of looking at scientific output for the facility. The reactor, The reactor is, so this shows you a little cutaway view or a perspective view of what the reactor looks like. The only thing I wanted to emphasize here is that I already mentioned we operate about 240 days per year. We're licensed through 2029. There are no life-limiting issues for the reactor, so we intend to license for another 20 years at that point. But the thing that I wanted to mention here is that if you think of a reactor like a light bulb, because a light bulb provides photons that allow us to see stuff, a nuclear reactor produces neutrons that allows us to see things, but see them differently. I'll explain that in a minute. But if you look at what the light bulb analog is of a nuclear reactor, in particular ours, it's like a Christmas tree light bulb. And so I just had a quick little sketch of a Christmas tree light bulb there. That's about the same amount of photons that come out of a Christmas tree light bulb. And what that means is we've got a dim source. And so we have to exploit every kind of neutron optical trick that we can, big detector coverage, big solid angle coverage of phase space so that we can measure as many neutrons as we can that scatter from the sample. So much of the innovation that goes on at the NCNR when it comes to the facility is in developing instruments that exploit being able to capture as many neutrons as we can. So one of the things that many of you may be interested in, if you want to get access to the NCNR, it's pretty straightforward. You can either get access through a general technical merit-based proposal system. So we have proposal calls about twice a year. And we have one coming up on November 10th here. And these are reviewed by an external independent panel, and there are no user charges. So this is considered a public good. It's a federally funded resource available to the US scientific community. So if you submit a proposal and our Beam Time Allocation Committee reviews it favorably, then it gets allocated beam time, and the only costs you would have, for instance, if you have to pay for travel costs, but at Morgan State you can drive to NIST, and it's basically cost of gas, I guess, to drive down. There's also collaborative access, and so this is still a merit-based access model, but it's where you can collaborate with our technical staff on problems of mutual interest. And then finally, there's proprietary use, where if the user wants to keep the results confidential, and sometimes industry likes to do this, then they will pay full cost recovery as required by Office of Management and Budget. I mentioned that access is pretty competitive, and so we typically have oversubscription rates of about, it's usually over a factor of 2, so we have to turn down of order 50% of the proposals, regardless of how excellent they are. We have to turn them down just because we do not have the beam time to give out. Okay, let's switch gears a little bit to the power of neutrons. I want to highlight 5, well, actually really 4 things. So in the upper left-hand corner, there's a little sketch of what the X-ray cross-sections are and what the neutron scattering cross-sections are for different atoms on the periodic table. One of the killer applications of neutron scattering is looking at hydrogenous materials. So think polymers, think biomolecules, things like that. Because the cross-section for hydrogen is enormous for neutrons, and yet it's something very difficult to probe with X-rays. There's also an interesting aspect of the fact that deuterium, which is an isotope of hydrogen, so chemically similar to hydrogen, it just happens to have a neutron. It has a tiny neutron scattering cross-section compared to hydrogen. We can exploit that for something called contrast matching, which I'll show in a second. The fact that neutrons have a small cross-section, or that lead has a small cross-section for neutrons but large for X-rays, is illustrated in the photograph below, which shows a neutron radiograph on the right-hand side of Asiatic lilies in a lead cask. So the neutrons just blow right through the lead, and they scatter, and you can see the contrast with the Asiatic lilies, primarily the hydrogen within them. So along the right-hand side at the top, you see that neutrons are a quantum particle, so they have a wavelength associated with them, like a de Broglie wavelength. And so you can use neutrons and the fact that they have a wavelength to probe structure through diffraction measurements. You can also use them for spectroscopy and probe molecular motions. And then the last killer application of neutrons is the fact that a neutron has a magnetic moment. So you can actually exploit that to probe magnetic structure of materials. And it's a unique way to do that. Just one quick sketch here as to some of the neutron properties. I just wanted to give you an idea of what the different wavelengths and energies give you. So in the bottom of that, you can see a thermal neutron, which is roughly a 2 angstrom wavelength. It's traveling about 2,000 meters per second. A cold neutron of order 6 angstrom is about 600 meters per second. And an ultra cold neutron is one that, about 400 or 500 angstroms. If you're really fast, you could actually outrun them. And these are all used for probing different phenomena. Now, when I come to the true stories told with neutrons and the scientific highlights, I'm going to be talking about 2 different types of measurements. One are structural measurements. and the other are spectroscopic measurements, basically probing the geometry of motion of your material samples. Now, the scattering geometry is common to both, shown above. So you have an incident energy and momentum, a final scattered energy and scattered momentum. And the momentum gives you information, or it comes from the direction in which you're scattering, and the energy tells you about the motion. And so just simple-minded ways to set up a neutron experiment are illustrated in the bottom two panels. Diffraction, you have a multi-wavelength polychromatic beam that hits a monochromator. So scattering from a monochromator, which is typically some sort of crystal like copper or silicon, will result in a very narrow band of wavelengths coming off of it. And then you scatter that from a detector, scatter that from a sample into a detector, and then you can get Bragg peaks, which gives you information on the structure. In a spectroscopic experiment, same front end for that. You have a polychromatic beam that hits a monochromator. Monochromator selects off a narrow band of wavelengths or energies that scatters from a sample, but here you take all of those scattered neutrons and you analyze the energy of them at the back end so that you can distinguish what the final energy is, what the initial energy is, and do a subtraction to get what the energy was either gained or lost by your sample. And that, coupled with the scattering direction of the neutrons, gives you all the information that you need to basically determine the geometry of motion of what's happening at the nanoscale of your sample. So I mentioned earlier about the fact that deuterium and hydrogen have very different contrasts. So this cartoon shows what I mean by contrast matching. So this character, Mel, is wearing, he's basically contrast match his outfit to the upholstery on the couch, okay? And what you can make out is his head, his arms, and his feet. And this is actually sort of what we do in neutron scattering to simplify our measurements. And so what I mean by that is this. We often measure samples that have multiple components to them. And so on the left-hand side here, I'm assuming that my multi-component system is composed of a core in the yellow, a shell in the white, and then the solvent is the violet. We can chemically treat our systems. Let's say it's a hydrogenous system, so there's lots of hydrogen in it. We can chemically treat the system and exchange some of the hydrogens on certain parts of the sample so that we can contrast match out features that we don't care to see. So in the upper right-hand corner, I can make that shell visible by matching it's called the scattering length density of the solvent to that of the core, or just basically deuterate the solvent and make it identical to what's in the core. And that brings out that makes the shell visible. We can make the core visible by making the material and the solvent and the shell identical. And so then that makes the core pop out. And we actually do this. This is something that's done in a lab. We do it in a nearby lab at University of Maryland at Shady Grove. And this is just a photograph of the laboratory that's a partnership with NIST, and it's called the Biomolecular Labeling Laboratory. And so we have access to this. It's also on a proposal basis, but frequently users of the NCNR are users of the Biomolecular Labeling Laboratory. Okay, so that was a whirlwind tour of history, the scientific user facility itself, and the power of neutrons. And so what I'd like to do now is, and I have to admit, this is my favorite part to talk about the applications of neutron scattering. I'm going to run through about 5 examples here. And I'm not an expert in the science that I'm going to show you because I didn't do this research. But let's just say I know enough to be dangerous. So I'm going to tell a few stories here. Okay, so the first story involves a solid-state chemist named Dr. Mas Subramanian from Oregon State University. And Mas is very interested in synthesizing materials for next generation devices. And so he's interested in phenomena called multiferroics, which involve interplays among magnetism and electricity and mechanical stresses and strains on materials. And one particular kind of, and he makes these things and then probes them with X-rays. One of the things that he was interested in finding out, because he thought they might have some cool properties, is combining YMNO3, which is a material that is antiferromagnetic and ferroelectric, in mixing that somehow with YINO3, which is a ferroelectric, and being able to tune the properties. And so you can see that one is the structure in the middle. So he sent his graduate student into the lab to synthesize this. They weren't sure if they were going to be successful. And so a day later, Moss checked with a student, asked how things were coming along, and the student says, well, I'm not exactly sure. I couldn't make a single crystal of the stuff, but take a look at this. And amazingly, Moss looked at this, and I mean, he saw exactly what you're seeing, a deep, rich blue. Now, what was so interesting was this was entirely unexpected, because the materials that went to make this were sort of a dull whitish, off-whitish. But when you mix them together, they created this blue. And Moss actually really honed in on that. And he was interested in this because he knew that no one had discovered a new pigment of blue in over 200 years. And this obviously was not his research area. Pigments was not his research area. I explained he was working on things related to next generation device technologies and what functional materials could be, but his curiosity actually got the better of him, and he wanted to know, where does that come from? Where does that blue come from? So he did some X-ray measurements. Don't worry, I'm going to get to the neutron measurement soon. But he did some X-ray measurements, and he was able to determine an overall structure to it, which you see on the left-hand side. Now, the Y and the O3 were actually, the O3s are all of the light blue atoms that you see, and then the indium and the manganese were in the dark blue in the center of that. And so he was able to get an overall structure that showed that really this material is made out of, they're called trigonal bipyramids. And just looking at that structure, you can see there are two pyramids that are sort of, their basal plane is shared. And so X-rays were able to give them the overall structure. And he did some further synthesis of it. And the further synthesis showed that if you change the concentration of the manganese in there, then you can change the shade of blue that you get, from a dull blue at the bottom to a very deep blue at the very top. And he surmised that this is due to crystal field splitting. So it's how those electron energy levels are actually split by the presence of the crystal field surrounding them. But he guessed that crystal field splitting is going to be due to the distance between that atom at the top, say the oxygen atom, and the compound, the indium or manganese that you have at the very center of the trigonal bipyramid. Unfortunately, with X-rays, you can't really get to you can't answer that question definitively. He needed detailed measurements to see it. And so this is actually where neutrons can be useful in what would traditionally be something that could be solved by X-rays here, because of the contrast that neutrons have of seeing the oxygens here. And in particular, he wanted to be able to measure the apical distance, the distance between that compound at the center in dark blue and then those two oxygen atoms that are both at the very bottom, and the very top, the apex and the zenith. So what he did was he also, along the way, had come up with the idea, what if I change the indium and manganese and replace that with indium, manganese, titanium, zinc, and aluminum? Just put something else in there, see how that changes. And guess what? He was able to come up with not just blue for very small amounts of, very small values of X, but he also came up with these rich purples. And the rich purples, this is where he really needed to understand, where is this color coming from? So he brought these samples to NCNR to do neutron diffraction measurements, so he could figure out what that dependence was of the spacing of the center compound from the apex oxygen atoms. And this is just diffraction data. If you've ever done a diffraction experiment or seen this in your solid state physics text, it should look pretty familiar. And so they were able to, from here, extract out with pretty fine detail what those parameters were. So looking at the plot on the left, in the lower left, what you can see is the change of concentration of the compounds in the center as you trade off between the manganese, indium, titanium, zinc, and aluminum, and how that affected both the basal distances, so that's in the plane of the base of the pyramid between the oxygen and the compound in the center, and the apical distance, and that's actually where you see where the really big changes occur. It's that apical distance. So using neutrons, he was able to determine how much that changed, and that was directly correlated to the changes in this case, the purples that they were reviewing. What's even more interesting than that, okay, so he had figured out what the origin of that color was, and it was based on that apical distance. But you know, another interesting facet to this is the near infrared reflectance of this, shown in the on the right-hand side, as you see the reflectance as a function of wavelength, was enormous, which means if you use this as a paint, then it's going to be reflecting heat. So you can imagine painting a roof with this and having a great deal of reflectance. And it's also environmentally stable and environmentally friendly. Okay, so this is a really cool story, in my opinion, because you know it started with serendipity, coming up with blue just completely out of the blue, and then being able to use some fairly straightforward materials research tools like diffraction, X-ray diffraction, and neutron diffraction to determine the origin of that color. But at this point, Moss was like a kid in a toy store, because he had come up with a way to change the colors. So two things to do. One, change the compound in the center of that bipyramidal structure. The other is use chemical pressure to change the distance, that apical distance, so you can run through different shades of the individual colors. And so this slide shows you how successful he has been going around the color wheel. Not just the shades of blue and purple, he got pink, orange, yellow, green, and all kinds of shades in between. One thing that is missing from that is red. And red is one that is fascinating, and it's been extraordinarily difficult for him to get, get using these techniques. But this past spring, I saw that he got a grant from the National Science Foundation to do a focused effort to try and get red. And that's important because currently red pigments have some toxic materials in them. And so you would like to use a technique like this to synthesize these materials so that they're not toxic and they're environmentally friendly. Okay, so that's the first example that I wanted to describe to you that tells a little bit about what we can do with neutrons. And it's also a fun story, and I should mention, if you're interested, you can hear more about the serendipitous nature of this on TED.com, because Moss gave a TED Talk on this discovery, which is pretty fun. Okay, next example I want to talk about has to do with one of our newest neutron scattering instruments, and it's called VSANS, for Very Small Angle Neutron Scattering. This instrument's huge. The detector tank had to be brought onto campus in 3 sections, one on each on its own flatbed. This flagship instrument is now very much in demand by our user community, and it's the subject of this highlight that I'm going to talk about, which involves researchers from Morgan State. But in order to give you an idea of the size of this, I mean, I think this tells you, especially seeing it on the flatbed, but in the lower left-hand corner, there are two of our technicians working on putting shielding on the inside of the tank. The one who is in the mid-ground, not the one who's in the foreground, is 6'8". So that tells you just how big the inside of that is. Okay, so this scientific highlight I really like, and I only recently became familiar with it, and it has to do with hexavalent chromium. It's an environmental contaminant. It's produced in industrial processes. It's carcinogenic, and as such, it's subject to federal limits. So it's really important to be able to measure hexavalent chromium to be able to assess for potential exposures to it. And methods exist surely for detecting hexavalent chromium, such as ion chromatography. This research focused on developing a system, hopefully, that would be able to detect trace amounts of it. So the Morgan State-led collaboration, which involved Seifu and Mercuria, focused on looking at the magnetic response of a magnetic nanoparticle intercalated carbon nanotube whenever it's infused with small amounts of the hexavalent chromium. And the reason is, the interest is in this nanocomposite system is based on evidence that these systems can exhibit enhanced magnetization. So a completely different phenomenon to try and detect hexavalent chromium, which has its own magnetic properties. So it's a really slick way to attach onto a different knob of a material, a toxic material, to make a detector. And so the question that they wanted to answer is the effect strong enough to make them viable candidates as ultra-sensitive detectors? To do so, they wanted to look at the structural and magnetic changes that occur when this nanocomposite has the hexavalent chromium infiltrated into it. And the VSANS instrument is able to help probe the structure of the intercalated magnetic nanoparticles, both with and without the chromium, when it's placed in a magnetic field. And since they were interested in the magnetic structure of the nanoparticles, they used the polarized neutrons to separate the magnetic scattering from the structural. And that's one of these other key killer applications of neutrons, is we can actually disentangle the structural, the structure of a material from its magnetic or magnetic structure of the material. And that involves using a neutron spin filter. So the schematic down at the bottom here shows you have an unpolarized beam of neutrons, which means the magnetic moments, or the north and south poles of the neutrons, just think of them like arrows, are directed all over the place. There's no preferred direction. When they go through the double V supermirror cavity, they all preferentially, whatever it goes through those are preferentially aligned. But then we can flip the spins in a magnetic field, and then it passes through the sample. And then when the polarization of those neutrons is changed by the magnetic structure of the material, we have to analyze that on the scattered beam, and we do that with a spin analyzer. And so I just wanted to show you what one of those neutron spin filters looks like. These analyzers, and basically you see that cylinder that says polarized helium-3. That contains helium-3 gas. So we're all familiar with the helium that's in balloons, helium-4. This is an isotope of that, and we can polarize this. And when we polarize the helium-3 gas, neutrons that are unpolarized that go through that will be polarized when they come out the other side. And so that's how we're able to determine the magnetism of the magnetic structures, by looking at the polarization as they come out. Okay. So that's the measurement technique. What did they find? Now, this slide is going to emphasize the neutron scattering results, but key parts of the research included also using a technique called vibrating sample magnetometry and extended X-ray absorption fine structure, XAFS. The magnetometry showed that whenever you put the chromium into these nanotubes, that the magnetization enhances by more than 70%. So it's a pretty significant increase. The XAFs also showed that you get structural changes just based on the fact that the chromium gets incorporated into the nanoparticles. But these are polarized SANS results that I show on this slide, and they show that the magnetization enhancement is not due to the nanoparticle length scales, so it's not a local enhancement of the magnetism, but it's actually attributed likely to longer range clusters of the nanoparticles. And this is shown in the top plots. These are intensity. So these are scattered neutrons as a function of direction as they're scattered from the sample. And that first point about the magnetization is shown actually in the upper two plots. Just looking at the ratio of those two upper curves, they're basically unchanged. And so what the researchers can extract from that is that there's no local enhancement of the magnetization. The other thing it shows is that whenever you apply a magnetic field and then take it away and look at the remnants, the nanocomposites aren't, there's no hysteresis in them in just the nanocomposites. But if they were infiltrated with the chromium, there is hysteresis, meaning that there's a remaining magnetic field. Now, this is really cool because I don't know if the researchers knew this going into it, but they basically were able to uncover two different routes that you could conceive of to use this system to detect the hexavalent chromium. One is looking at the enhanced magnetization, which seems to be a fairly straightforward effect and borne out by the data. But also the fact that there's a remnant effect. There's a remaining magnetic field after it's been infiltrated with the chromium, and then you apply a field. So I like that because that's a really nice example of a potentially quite practical application of neutron scattering in functional materials. Okay. Next technique I wanted to describe to you is neutron reflectometry. And this, like diffraction, is a relatively straightforward measurement technique. It's illustrated in that top plot where you can see a slab of material of depth L and a neutron illustrated as a plane wave coming in and scattering. That's angle of incident equals angle of reflection. So we're talking about a purely specular reflection geometry. And what this gives you, if you look in the reflection pattern down below, and this is like what you would measure in an experiment, is an oscillating pattern. And those oscillations give you very detailed information on that depth L. You can extract L from that. And you can imagine if you have a complicated structure, not just a scattering from a slab, you can actually extract, you'll have a very complicated diffraction pattern down below, but what you'll be able to do is extract out what that layer structure is. And I like these measurements conceptually just because you're solving a one-dimensional Schrodinger equation and extracting out a whole wealth of information from that. And these are also fun to simulate. So let me talk about an application of this. And this is one that is admittedly quite far afield from my own solid state background, but I really like this example. And this just was published in September. So there's a gene called KRAS that provides instructions for making a protein, also referred to as the KRAS protein. And it's important because it's responsible for relaying instructions from the outside to the inside of a cell. And in particular, it tells the cell whether it should grow and divide or mature or take on other functions. So the protein acts like a switch that's turned off and on by particular molecules in its vicinity. The reason why it's important is that some cancers arise from mutations of the KRAS gene. And in fact, KRAS is implicated in 1 in 7 of all human cancers, including lung cancer, colorectal cancer, and pancreatic cancers. So a research team from CMU, NIST, and a host of other institutions recently used this neutron reflectometry technique, NMR, and computational methods to look at the mechanical mechanism that underlies the switching function of the protein. They made a tethered lipid bilayer, which mimics the cell membrane in a KRAS protein as well, and used neutron reflectometry to look at the structure. What they found was really neat. It was known that the switching mechanism requires KRAS to recruit one of these binding partners or molecules to the membrane surface, but they didn't know how it did that. So they were able to use neutron reflectometry, and the data is shown, or the structure that they extracted from the data is shown along the right-hand side, but they found that KRAS protein adopts what's called a hanging heart conformation near the surface. And it's configured almost like a lure in fly fishing that attracts a fish to the water's surface. And it's trying to attract this RAF kinase to the surface to be able to affect the switching mechanism. I just was really brief in explaining what they were able to extract. This was a measurement and computational tour de force to just get that information. And, you know, admittedly, this is a simplified artificial membrane that they used, and it models the complex plasma membrane. It's limited in what it can do, but this surface sensitive measurement technique is very attractive and unique way to obtain very useful information on biophysically relevant systems. And this example actually shows that pretty clearly, I think. Okay, it looks like running pretty short on time here, so I'm just going to go through one more example here. And this one has to do with e-cigarettes and vaping. We know that this has been in the news quite a bit. E-cigarette and vaping market was $12.4 billion in 2019, and it's expected to grow through 2027 by 24%. What's been in the news, unfortunately, is the injuries that have been associated with vaping. In February, the CDC reported there have been more than 2,800 hospitalizations and deaths in the U.S., and the condition is known as EVALI, E-V-A-L-I, or electronic cigarette vaping associated lung injury. And the suspected reason for the type of injury is an additive that's put into the vaping fluid, vitamin E acetate. And it's an unfortunate irony that the manufacturers actually put vitamin E acetate into the e-cigarettes to preserve lung function. Anyway, the mechanism by which the vitamin E acetate affects lung function has been a matter of speculation until now. And so a research collaboration between NIST and the University of Windsor aimed to shed some light on this. So I'm going to talk a little bit about, I need to talk a little bit about the lungs. And so in the lungs, there are these air sacs, they're called alveoli, that allow rapid gas exchange. Encoding these air sacs is a monolayer of something called a pulmonary surfactant. And if you're familiar with surfactants, you know that primarily they lower surface tension on what they're covering. And this is no different. This pulmonary surfactant lowers surface tension in the air sacs and allows you to easily inflate the lungs. But there's also a balance here too, because when you exhale, you want the surfactant to maintain stability whenever you exhale, so that they're not just maintaining rapid absorption of the gases, but you want to be able to exhale and not have that monolayer collapse. How it does that is very hotly debated, but what is uniformly agreed to is that the elasticity of that thin membrane of the pulmonary surfactant is going to be critical to understanding that. And this is where neutrons come in, because frankly, there is no other technique that gives you access to membrane fluctuation. So this is a very simple schematic of a membrane illustration, or membrane, a lipid bilayer. So there's several ways that this can, you can have motion on this. There's bending fluctuations that are shown there, annotated, stretching, protrusion, and thickness fluctuations. And neutron scattering actually sits right in the sweet spot of how we can measure those membrane dynamics. So this is this rather busy plot. I'll just draw your attention to the x-axis at the bottom, which is length scale that we probe in meters, and the left axis, y-axis, is the time scales we probe. Neutron spin echo allows us to probe large-scale slow motions, and you can see that bending and thickness fluctuations are right there in the sweet spot of neutron spin echo and not accessible by others. So this is what the spin echo spectrometer looks like at the NCNR. You saw this before. Since we're short on time, I'm just going to very briefly explain the principle of operation. This is a spectrometer, so we need to know the difference between the incident energy and the final energy of the neutron, so we can figure out the energy gained or lost by the neutron. And in this case, we treat the neutron like a clock. And remember, it's a polarized neutron. Points in a direction. So we polarize the neutrons, it's pointing in a direction, we tip it, put it through a magnetic field in the first green arm on the left, and it processes like a clock, and that's how we keep time. Scatters from the sample, and it either goes faster or slower through that second arm, depending on if it gained or lost energy. And we just look at the time difference between the first leg and the second leg, or how many times it's processed, and that gives us information on the energy exchange. And in particular, we measure a time correlation function. So this is the actual data of the experiment. They all look like decay curves because the correlation just decreases over time. But the important part is how this is modeled. These are modeled as stretched exponentials, and the stretched exponentials are the model used for a thin sheet undergoing membrane fluctuations, which means from this data in the curve fits, we can extract out what the bending modulus is of the membrane. So we can access that information that we so dearly wanted to get to be able to determine what the impact on the mechanical structure was and the mechanical function of these membranes are based on the addition of vitamin E acetate. And that's what this plot shows. This one shows you the bending modulus, K, or kappa rather, as a percent of how much vitamin E acetate is added. And in particular, I just want you to look at the red circles here. And they show you that there is a precipitous drop-off in the bending modulus when you add even a little bit of the vitamin E acetate. And what they extract from this is the membrane rigidity decreases when you add the vitamin E acetate. It increases the membrane fluidity, and this suggests that the lung surfactant actually could squeeze out the lipids in it prematurely during exhalation, whenever you breathe out. And so that means that this could be lead to the instability. So the authors, they hypothesized that the vitamin E acetate-induced membrane softening promotes the failure of the surfactant whenever you exhale. And they are surmising that this does indeed offer a mechanical explanation for the lung dysfunction found in the volley. Okay, I have gone fairly long, and I do want to be able to take questions here. So I'm going to just leave my last slide up here. And also it shows the website for the NCNR. And I encourage you, if you're interested in learning more about what measurements, how we can help you with measurements of your research projects, to reach out to us, and certainly reach out to me. So I'm going to actually pause this presentation and go to my camera.
Okay, Rob, while you're doing that, I have 3 comments to make before I turn it over to Dean Yu to lead the questions. First of all, you're having too much fun, man. And second, I noticed that you did find a way to slip in some of your sketches. And third, before you go, can you mention something about the Prompt Gamma facility? You know, I still think I'm an old analytical chemist.
Absolutely, and yeah, I apologize for the sin of omission there, but the Prompt Gamma facility is really interesting and allows us to do different things than just neutron scattering. Prompt Gamma is an analytical chemistry tool that allows us to take all kinds of samples, made up of different chemical constituents, and then be able to extract with exquisite sensitivity trace amounts of different elements. And this has so many applications. One is in standards development. Another one, which is fascinating, is in a partnership with the Smithsonian Institute. They're heavy users of that. They actually have been able to start rewriting textbooks on trade routes of South American tribes because they're able to trace the trace elements or trace the pathways based on pottery shards that are found in different parts of South America and Central America and determine the origin of where they came from. So it's a really neat application of doing this exquisitely detailed and precise trace element analysis. I hope that was okay, Willie.
Okay, that'll do. Dean Yu, the show's yours.
Right, although I attended late, but I just want to thank you for such an outstanding presentation. I would say let's give Morgan a warm thank you for your presentation.
Thank you very much.
I would just relate to Dr. Ramesh Bodani for the question and answer session. Dr. Bodani is a professor of physics. I don't know whether he used your facility or not. I don't remember. Did he use your facility? Oh, he did. Okay, so that's good. So he can ask a question. But before I go to him, I have a question I need to ask you. Number one is about, I missed the beginning, of course. Could you describe to me the major difference between the light scattering, the photon, and the neutron scattering that's manifested in some of the experiment techniques?
Yeah, so the major difference, basically we see neutrons see things differently than light. And I had one slide at the beginning, I apologize if you weren't able to see that one, that actually shows the fundamental difference. I lined up neutron scattering cross-section of different elements from the periodic table and X-ray scattering cross-sections. And so one big example, Dean Yu, is that hydrogen scatters scatters neutrons really well, whereas it doesn't scatter, since it's a light element, doesn't scatter X-rays very well, okay? We use that actually to do, I mean, most of the examples I gave, or many of the examples I gave, like with the pulmonary lung surfactant, the KRAS, these things all have hydrogen in them. And so we exploit that to see them, both structural and dynamic information from them. That's one example. Another key advantage of neutrons over X-rays, the fact that neutron has a magnetic moment, and so we can see fairly directly magnetic structure. And then finally, I would say this ability for neutrons to go through metal much easier and opaque material much easier gives us a decided advantage over optical techniques and X-ray techniques, because we can use our high pressure systems, for example. They could be made of really chunky metal, our cryostats, things like that, our furnaces. I mean, there's ways to do that with X-rays too, but there's an advantage in the complexity that we have with our sample environment systems.
Follow up to that, I saw your detection for chromium 6. Would that be able to distinguish chromium 6 from chromium 3?
I'm sorry, what distinguishes chromium 6 from?
He asked if you could distinguish chromium 6 from chromium 3 using neutron applications.
Oh, I see. The top of my head, I can't answer. Yeah, I'm not sure. Sorry.
Okay.
Maybe that's an experiment to propose, Dean Yu.
All right, Dr. Bodani, thanks. Sorry for starting this. Thank you.
Dr. Daniel, thank you so much for this very interesting lecture. And I'm going to take the liberty to ask a couple of questions myself. since you are also involved in the management of the facility, the first question is policy related. And I'm wondering if you have some special consideration for beam time allocation to students, undergraduate students, because they cannot really compete with these, with the rest of the, it's really difficult if there is no special time allocated for student research. So I'm just wondering if you have any thoughts in that area.
Yeah, absolutely. We actually have quite a few opportunities for students. One is just our annual education opportunity of our summer school. We have a partnership with the National Science Foundation, and as part of an important part of that, the centerpiece actually of our education and outreach program, an annual summer school where students will come for a week to do experiments, learn about the neutron scattering technique, and do some relatively straightforward experiments, both in spectroscopy and structural measurements that allow them to learn the technique. But I think your question was more focused on actual research projects.
Yes.
We do have a few neutron users, well, neutron investigators who bring their students to work on experiments too. So that's another access mechanism. And then finally, for undergraduates, we have something called the SURF program, which is like the equivalent of the REU program that you have at many universities, the research experience for undergrads. So undergraduates will come and spend a summer with us and actually do quite a few experiments, data analysis, and things like that, with a principal investigator actually from the NCNR. So these are some really in-depth experiences that they get learning the technique. And I love this program because we see them coming back perhaps in graduate school and going on to be young faculty members in industry too. And then they know the neutron technique and what it can offer them in their own research programs.
Rob, let me jump in a second. Morgan colleagues, I urge you to do this. And looking over some data when I knew I was coming to Morgan, I checked back with some of my colleagues. There have been few, if any, Morgan students that's taken place of that. That program takes in about 200 kids competitively across the United States each year. And it is an absolute shame and an abomination that Morgan, so close, has not taken advantage of this. As Rob says, this has launched the career of many young scientists. And again, in his facility, you would gain some unique knowledge. Not only do you plan to maybe come back and explore a career, maybe talk to some of the people that are about getting involved through the prep program. There are just so many advantages that one could gain by having our students be selected to participate in the prep program, at least in the CERT program.
Yes, I have Dr. Bill wants to ask a question. Please go ahead.
Thank you. Rob, great presentation. Thank you. I really love the tools. It's a great way to combine with scientific work. Just a comment first, ask a question. So my son is also a doctor. So kids.
Dr. Oster, can you get closer to the mic? I think we're having a difficult time hearing you.
Okay. Can you hear me now better?
A lot better.
I think there is also like an echo if everyone else can mute. Okay. All right. I'll repeat my suggestion. So Rob, can you hear me?
Yes, still a little weak though.
Okay. Well, I'll try to make that comment. If not, I'll write it in the chat. But I'll ask everyone else to mute, please. There's a background sound. Can everyone else mute, please? Okay. Can you hear me better now?
Yes.
Okay, good. So I really love the presentation. Thank you. It's great that you combined your passion for doodling with your work. So my son is also a doodler. So I think you should make a video, because like kids who can doodle, although they are great in science, they like to become a digital artist. So I think you're a great example showing that, you can combine your, art with your scientific work. If you make a YouTube video and show your work and your, title, what you are doing, I think it will be great for the younger scientists. So my question is, I hope you can still hear me.
Yes.
Okay, my question is about this color centers in diamonds or defects, quantum defects in solid state materials. So do you have this neutron diffraction? Does it have the resolution, high resolution to probe single spins at this, single spin level? Its magnetic characterization or structural characterization. Does anyone do like a work like that? Do they look at this, color centers in solid state materials?
So I am not that familiar with work with neutrons in that, which may mean, unfortunately, I can't answer your question based on detailed knowledge of the application, because in principle it should be possible, but I'm guessing, because I don't know of any major examples of that with neutrons, that it might not be practical to do that. Yeah, but I'll think about that some more. And then regarding your first comment, thank you for the feedback on that. I actually, since I've been combining science with science communication and doodling, I've taught workshops on how to take visual notes at NIST since 2016, I think. And so I've trained probably about nearly 500 scientists and administrators at NIST in the technique of taking visual notes. And every summer I show stuff to our undergraduates and high school interns as well, and they like that.
All right, the next question is from Dr. Alex. Alex, can you please ask your question?
Good morning, everybody. Can you hear me well?
Yes, I can hear you.
Dr. Dimeo, first of all, thank you very much for the beautiful presentation. What I particularly love about this is physical chemistry background or instrumentation background, because I kind of physical chemist by myself. I love doing spectroscopy, and although I never did neutron scattering specifically, I did XRD and a lot of molecular spectroscopy by photons. And with this thing in mind, I'm also doing material chemistry, something called metal organic framework here. So I was fortunate to get few extramural grants this year from federal agencies to study metal organic framework interaction with molecules. This includes structural studies. And I would like to inquire if NIST has scientists interested in this already, and all the capability of doing specific kind of neutron diffraction research with chemistry. And with this thing in mind, if I have up to 5 minutes or so, can I switch to a little paper with handwriting to show my chemistry and ask whether this can be done by the neutron scattering? With this thing in mind, let me disappear from screen for a little second. I put my paper on the screen, if you don't mind. Let me just try to do a little
Well,
wait a minute. Let me. Okay, so now this is how I'm actually teaching students, because
if you write your question on chat, I can read it for you.
Yes. So here is my chemistry. Let's say I have porous material like this. This is nanopore. And let's say there is some, let's say 7 angstrom from here to here in the pore. Okay, let's say there is some hydrogen here and some carbons and things. And let's say this is breathable, it can shrink the crystal lattice when the molecule X coming inside. Let's say due to some kind of chemistry, let's say this is MOF, metal organic framework, inside pore, and this molecule, which is external molecule, somehow comes inside due to some kind of chemistry. And let's say now it's sitting here, and this has also hydrogens in it someplace, here in Earth. Let's say now it starts interacting somehow like this, with this or this. And let's say due to intermolecular forces here, it changes the shape, now becoming something like this. Let's say it becomes flat like this. And after becoming flat like this, I still see this X molecule inside here and interacting somehow with this, and this. And again, there are hydrogen atoms here connected to carbon and things like this. And now it's a flat, and it used to be, let's say, rhombic shape before. And my question is, if I use neutron scattering, can it answer a couple of questions? First of all, can I see the structure by the scattering? And second, can in situ, real time, of the same, of reaction, of framework with this, with the molecule? And the third question is, you know, somebody already doing this.
Okay. Yep. Yeah, I got it. Okay. Okay. Can I respond now?
Yes, please.
Okay, so the answer is a very enthusiastic yes. We actually have quite a long history of doing measurements on metal organic frameworks, especially when species that are placed into them. Hydrogen, methane, all different kinds of chemical species. And in particular, we have looked at not just the structure, but also the dynamics of what you have when you have these guest host species. The particular question is if you can see the structure, the major structural changes as well as the internal changes is detail that in principle we can access with different techniques. So for instance, small angle neutron scattering can get you the longer scale structural changes, whereas the should be able to get you the internal structural changes. It seems like your length scales are on the smaller side, so what I would recommend is you talk to, you want to write this name down, Craig Brown. Dr. Craig Brown. He's a NIST fellow, and he spends an awful lot of time working on metal organic frameworks and what the structural and spectroscopic changes are, dynamic changes are when you put different species inside of them. Thank you for the. That's
okay. So I move on to the next question. Can I? Dr. Rispi has a question. Please go ahead, Dr. Rispi.
Hello, everyone. Hi, Dr. Dimeo.
Hi.
Thank you so much for your nice presentation with all this information. So I used neutron scattering 6 years ago with Peter Gehring, so to study some iron alloys. I mean, basically, they are in the bulk phase single crystal. So my question to you, just to make it simple, we study films, basically magnetic films, especially oxides. And we want to know, like, the boundary, for example, what's happening at the boundary. Usually, like, there is like a spin fluctuations at the boundaries, or there is a random distribution of spins due to competing interactions at the boundaries of magnetic oxide of magnetic films. So my question to you, is it scattering can help to determine these boundary structures or the spin configuration at the boundaries?
Dr. Lisfi, have I got an instrument for you? We have a brand new neutron reflectometer called Candor. And this instrument is a very high throughput, high intensity neutron reflectometer that allows you to be able to, I mean, it really emphasizes being able to hone in on magnetic structure with polarized neutron beams at interfaces. And we have one particular researcher that comes to mind named Alex Grutter. He is a relatively young scientist who has done measurements of the magnetic interactions at boundaries and looking at the spin structure across boundaries. So I think this is, and Peter Gehring also obviously knows about this stuff too. But if you want to send me an email message, I'm happy to send you his contact information as well as some references of these measurements. But that is doable. They are difficult measurements, but you're not going to be able to do it without neutrons, and we have done that. Thanks for the question.
Well, there's a question on chat from one of our students, Bilson. It says, when probing on the surface of cells, are there any limits about the thickness of the cellular membrane?
Okay, so that's a good question, and there's a couple ways to answer that. Remember I showed you the, I used the word sweet spot for where membrane fluctuations fit within the dynamic range of a neutron spin echo spectrometer. If you have a membrane that's too thick, the motions could become too slow. If it's too thin, they could become too fast, and then they would be outside of the dynamic range of the neutron spin echo spectrometer. So simple kinematic constraints may keep you from being able to probe the system. But the question, that's an experimental feasibility question that you would talk with one of our instrument scientists and say, hey, look, I want to measure this system. Is this feasible for spin echo? And they may actually have some good ideas as to how you could synthesize a biomimetic membrane that is within the dynamic range of the instrument we have. So thanks for the question.
I have a question about helium-3 spin polarizer you talked about. Are you using helium-3 or is something else?
Are we using helium-3 gas? Is that your question?
Helium-3 ice or you use helium-3 gas?
Oh, no, not ice. No, helium-3 gas. Yeah. Well, helium-3 ice is kind of hard to make with a lot of pressure on it. But helium-3 gas, and it's kind of cool how these are made because they're sealed quartz cells that are about that big, and they've got rubidium vapor coating the inside surface, and then inside of the cell, of course, is the helium-3. Lasers are used to pump the rubidium gas into an excited state. So that you get those spin polarized moments, and then they spin exchange. They exchange their spin with the helium-3 nuclei, and so we pumping offline, and then bring them on site, bring them onto the beam line, and they work. It's cool.
And the polarized state stays for a long time.
We have the world record for
moving at random, right?
No, they do depolarize. No, absolutely, but we record for, and not just the amount of polarization, of order 99%, but also the fact that, there are so many things that go to depolarize the helium-3 gas that you have to be very careful with the fabrication of your cells. And so we've got it down to form where usually it's every couple days we have to swap out a cell. So we have spare cells that have been optically pumped and ready to go. We put those on the beam line. And the data analysis software actually corrects for the depolarization over time during the measurement.
Oh, thank you. Well, are there any other questions? Anybody have any question to ask?
I have a comment.
Yeah,
and I guess it's a question also. And Rob, I guess, and I don't want to put you on the spot, and you don't have to answer this now, but I wonder if you would not consider having NCNR get engaged with the prep program. Morgan has a prep program through Morgan. It's $1 million a year IDIQ. So if there is some research that needs to be done there at Morgan, you can essentially engage with our faculty and students via that mechanism. It's already approved administratively. It just needs to find a need from your perspective, and then off we go. So I'll leave it at that.
And I will say, let's talk some more. Okay? Happy to.
Well, thank you so much for taking all the questions. And actually, I'm also collaborating with Brian Kirby, doing some experiments on magnetic thin films with him. And the beamline proposal is due, I think, on the 10th. So we are working on that, on a new proposal. Yeah.
Terrific, terrific.
And thanks also, Rob. Thanks for that seminar. I've been trying since I've been here at Morgan to educate some of our faculty and students about what NIST really is, because as you know, being there, that the what, and it'll always be we to me, what we actually are there is a bit different than most people see when they hear the title National Institute of Standards and Technology. They see somewhat of a bureaucratic organization rather than basically a federally funded research university.
Yeah.
So thanks for beginning to bring that out without any prompting from me.
Well, you know, Willie, you've always been like family. So I heartily endorse you saying the royal we. I'm sorry that it didn't work out. I was hoping to come in April or May to give an on-site seminar, but obviously the circumstances in the world prevented that from happening. This has been a great opportunity. I really appreciate all of the questions. And I strongly encourage you folks, if Willie can share my email with everybody, if you have any further questions, don't hesitate to reach out to me. I'm happy to talk more, give you referrals to different people who are doing research in areas that you're interested in. So please do, and thank you.
Thank you so much, and thank you, Dr. May, for introducing the speaker. Thank you.
Yeah, I do want to say a word before we leave. Rob, thank you so much for the presentation, and at least made me understand what kind of neutron scattering techniques can be used for research. You know, the detecting chromium-6, as well as the cell membrane study. I'm very impressed with those results. So in your collaboration with all the universities there. So here we're neighbors, really need to take advantage of all these to work on. You know, we're going to develop some proposal with some of the people at NIST. And in addition to that, we want to encourage our students to really, students and faculty, to really use the facility.
That sounds great.
I have one last question, if non-technical, and this is Daraja Saifu. I was at the NSPP. I'm chairing a session on international engagement, and I only caught the tail part of this talk. Is it possible to get the recorded version so we can I can look at it later on?
Yeah, John has I think John recorded, right?
Yeah, when I logged in, it says recording.
That's correct. This meeting is recorded, and I'm going to share with Dr. May and Keyshawn, and it'll be posted on the DRED website.
Great, thank you.
Thank you.
And also, we will try to sort of collect the questions in the chat and combine them, and then work with Dr. Dimeo to provide answers to those. So it won't be like FAQs, but we will again accumulate the questions and then post those and make sure we have responses to those.
Thank you.
Thank you.
Thanks all. Okay, have a good day.
Thank you.
Thank you.
Thanks again, Rob.
Bye,
Thanks so much, man.
Thank you,
Thank you
everyone.
so much.
Thank you. Thank you.
Thank you, everyone, for attending, and especially thank you, Dr. Dimeo, for sharing your time and your knowledge and letting us know about the resources available at NIST and the neutron studies.
My pleasure.
And Rob, as soon as I can get to our bookstore, I've got a Morgan Under Armour shirt for you.
Okay.
Thank you.
Bye.
All right. Bye-bye.
Bye.
Bye, everyone.